Tree is a storage structure that consists of a finite set of elements. These elements are often called nodes, and then a set of lines or interconnections that connect the nodes together. These lines go by different names such as arcs or branches. The nodes contain the data of the tree. They are composed of a payload element, that is the data value, and then pointers that are used to create the lines or the arcs connecting the nodes together. Depending on the type of tree that we encounter, these can go by different names. In a binary tree, for example, these are called leaves. Leaves are the outer elements of a tree. That is, these are the peripheral or the tertiary, the terminal ends of the subtrees. They contain no other attached elements. The base element, which begins the structure of the whole tree, is called the root. The tree finds a lot of uses in computer science and in algorithm design. For example, putting together mathematical formulas by putting different elements of the, say, algebraic notation together in order to process that formula properly. It's used for searching lists because we can create a binary structure that subdivides the amount of data together and searches it very efficiently. It's used in artificial intelligence systems. It's also used in compression algorithms. The Huffman encoding algorithm uses a binary tree method in order to do zip encoding. A binary tree is a specialized tree in which each subtree is only composed of 3 nodes. That is a root or a subroot, if you want to look at it that way, and then 2 nodes, one less than, one greater than the top node. In this sample that we see in front of us, the top node would be the root element. Everything to the left of that root element would be less than the value of the root. Everything to the right is greater than the right element. If we fill this in, we have a set of state abbreviations, and we'll apply them in the order that we receive them. So either user input is being applied, or data input from a file, for example, is being applied. So the first one we encounter is Idaho. That would create the first node of the list. And then we take and compare each of the succeeding elements against that data value. So we take Colorado. Colorado is less than Idaho, and so it goes down the left subtree. Utah is greater than Idaho, and so it goes off on the right-hand subtree. Now when we encounter Kentucky, we have a couple of jumps that have to occur. First, we compare Kentucky against Idaho, and it says go to the right subtree. When we reach the node Utah, we compare Kentucky against Utah, and we find that it is less than Utah. So it would be placed in the left-hand subnode, or the left-hand part of the subtree, underneath Utah. Likewise, Washington. Washington is greater than Idaho. Washington is greater than Utah, and so it belongs on the right-hand side of that subtree. And we just keep adding data in this manner in order to fill up the binary tree. Now, if we go and search, we follow the same exact process. We are going to look for Kentucky in this list, and so we start by approaching Idaho. Idaho tells us that Kentucky is greater than Idaho. So it says to go check the right-hand subtree. We reach the first node, and it is Utah. Kentucky is less than Utah, and so it says follow the left-hand subtree in which we find the item. Now we're going to search for Delaware and see a little different condition occur, and this is how we discover that something is not in the list. We are going to compare Delaware against Idaho, and because it is less than Idaho, we are going to traverse down the left-hand subtree. So we arrive at Colorado. Delaware is not equal to Colorado, so we ask, is it less than or greater than? Because Delaware is greater than, we go and check the right subtree. Now, because Colorado is a leaf, it is on the outside or the terminus of the tree, both the left and right pointers are going to be set to null. And so when Delaware attempts to traverse down the right-hand subtree, it's going to find that the value of the pointer is null. There is no subtree, and that tells us that Delaware does not exist in the list. It is impossible for Delaware to be anywhere else in the list because of the binary logic that we use to place the items in the list in the first place. Binary trees are very efficient as long as they are balanced. When a binary tree becomes out of balance, it becomes very inefficient. We have a set of data elements, again a list of state abbreviations listed down the left side there. If we place those items in the list, we're going to find that we create a very out of balance list because the data items are already in order. So Alaska gets placed as the root node. Then we take Delaware, compare it against Alaska, and it is greater than Alaska, so we go down the right subtree. Florida is greater than Alaska, Florida is greater than Delaware, and it goes down the right-hand subtree. Hawaii, Indiana, Kentucky, all follow the same path. And now what we have is a terribly out of balance binary tree. A binary tree is considered to be out of balance when the levels, that is the number of subnodes down the list, are 2 or more levels higher than the corresponding subtree. In other words, Florida would be the furthest we would want to go from Alaska when we begin to call this list out of order. And so a balancing algorithm is often used to balance out a tree. And what we do is take subtrees and rotate them in order to bring things back into balance. The middle node of the string of nodes there is rotated up to become the root node. Since the item above it has to be less than that element, it gets rotated off to the left. The subsequent item, the Florida node, is greater than, and so it gets pushed off to the right-hand side. If you have built any kind of a linked list, building the binary tree is not too much of a challenge. It's pretty easy to understand, and it uses very familiar concepts. The node that we use contains an additional pointer, one more than you would normally use in a simple linked list. And these 2 pointers point to the left-hand side and to the right-hand side. Every single node in the tree uses exactly the same structure. So we define a struct called state node, and then we define the payload type. In this case, it's a string, but it doesn't have to be. It could be another substructure. It could be a string, and it doesn't matter. Whatever the payload value is, you would put that inside of your node structure. And then the 2 pointers pointing to the next node down the list. When we initialize each of these nodes, we're going to initialize those values to be null, so that as we apply each new node into the list, it becomes a leaf. That is, it is without anything attached to it, any subtree attached to it. Adding a node into a binary tree, a simple process. There's just two things that have to be coded. Number one, you have to follow the subtree down. That is, you need to keep either recursively or iteratively walking down the tree until you arrive at a leaf, because that's the only place that you can insert a new node. So you loop, loop, loop until you find a leaf, that is a pointer that equals null, and then you attach the new node back to either the left or right pointer of that leaf. Here's a very simple pseudocode representation of the process. Number one, we check to see if the root is null. If it is, we just start a tree. That's very simple. So we're going to go out, initialize one of those state nodes, set the left and right pointers to null, and that gets passed back as our root value. Now, unless we're rotating the list, unless we have a balancing algorithm, that root node pointer is never going to change during the execution of your program. If it's not null, that means we have at least a root node, if not more, in the subtrees. We start walking the pointer down. So the walk pointer gets established to the bottom of the tree, to the root value of the tree, and then we loop until we find a null, simply stepping down the subtree according to the greater than or less than algorithm, and then we check and see if it's null. If it's not null, we walk further. If it's null, we walk further. If it's not null, we walk further, and so on until we find a leaf. And then when we finally have found a leaf, we establish a new node. And then lather, rinse, repeat. That's all that's necessary to add a node into your binary tree. The only evaluation that is occurring throughout is this greater than or less than the current node that I'm looking at? We're going to walk through some code of a very simple binary search tree program. We see when it executes, it shows what's in the binary tree in order, so it's doing that in order traversal. And then it simply asks for items to search for. So if we search for Oregon, we see that it is located in the tree. If we search for Alabama, we find that it is not in the list. So let's go back and have a look at the code. The code itself is very simple. It's not going to be too complex to understand. We start in main. We establish or initialize our root to null. And then we load the states. Load states is a file processing function. So it's going to open the data file. This data file that contains the state abbreviations. It's going to open that file and simply loop until end of file, calling add node each time so that it reads the item from the data file and then adds it as a node into our binary tree. So we're going to take add node, and I'm going to drop a breakpoint here so that we can trace through the building of the tree. So we execute the program, and we have started by getting the first value in here. We see that inString contains the first value Idaho from the data list. And so it is evaluating to find out if the root pointer, in pointer, is null. Since it is, it's going to establish a new node. Now you should verify this, but for simplification purposes, I did not. So it establishes the new memory location, puts Idaho in as the payload value, and then initializes the two right and left pointers to be null. So this essentially is creating a leaf, even though it is the root value. It's done, it goes back, it gets the next value, right? So we're reading the second value, Oregon, and checking to see if it is to the left or to the right of the list. We set the walker, or the variable that we're going to use to traverse the list. And while it's not equal null, that is, it has not reached a leaf yet, we go and start examining the subtrees. So if the in string is less than the state that we're sitting on, which is Idaho, then it is going to go to the left. If it's greater than, it's going to go to the right. So Oregon is greater than, it's going to walk down to right. And then it's going to loop around, and it's going to see if there is an additional subtree that needs to be examined. And now it is out at a leaf position. It creates a new node and then adds it in. Again, once more. Okay, so we've read a new value in. It's not null. We start walking until we reach a leaf. We start at the base. Check against Idaho. We're going to the left this time because our new state after Washington is Arizona. And now we're going to the left. Since we haven't added anything to the left, we only have to traverse the one part of the subtree. We step down, establish a new node. And then after we have established that node, it's important to go back to the parent, that is the preceding node, and make sure that you connect your new node back into the subtree. So we put this on the left, return the root. The search, you can see the code here is very simple. It basically sets up a loop to see if we've reached either a value that matches or we've reached a leaf point, that is, the pointer equals null. If we've reached a pointer equals null, then we know that we have traversed the correct path through the trees and that item does not exist. So we'll execute this once again. And in this case, let's look for one that we can find. Okay, so we're back in here. We know that the root is not null. That is, it's not an empty tree. So it's going to drop down to this while loop. While in root not equal null, that is, does it continue to move forward? Okay. So now we're going to examine the search value, which is Arizona, and see if it equals the state. It does not, because we're sitting on the root node, so Idaho is not equal to that. So we're going to set down. We're going to see if it is less than the state. Arizona is less than Idaho, so it's going to go to the left. So we set the new pointer to the left pointer and come back out. Now, in root's probably not a good choice for a variable. You would want to use something like a looper or something more descriptive. But we step in. Does it equal, does search value equal state? In this case it does, because it was a very short left subtree. If so, we return true. The program says the state was found in the tree, and it goes back and gets another one from the user. So in this case, let's look for Hawaii, which we know is not in the list. Okay, so we step in. We know it's not an empty loop or an empty tree. Search value not equals Idaho. Okay. So since we know we need to move down the subtree, we're going to check to see if Hawaii is less than Idaho. H is less than I. So it's going to take the left path. Okay, it's on Arizona. It's not equal to the state. Now, if it is Hawaii is less than Arizona, it is not, so it's going to go to the right subtree. In root is going to take the value of in root right, so it's going to loop through once more. Is Hawaii equal to California? No. Is Hawaii less than California? No, it is greater than, so it's going to come down to the right subtree. And in tree right equals null, because there's no subtree past California. And so in tree is going to get null. It's going to loop up. And now that we've reached null, we know that we have reached a leaf. That is, we have reached a terminal value in the tree. And because we have not found what we're looking for, and we have reached a terminal value, using the binary tree logic, we know that that item does not exist in the list. And so we return false because no match was found. We report state not in the list back to the user, and we continue on. Once you have filled your binary tree with data, you're going to want to generally do something more than search it. And that's oftentimes you want to traverse all the items and either view them, print them out to the screen, or utilize the data payload in some fashion. So there are a number of ways in which traversal can occur depending on the outcome that you want. That is, the order in which you want to use the data. In-order traversal processes the tree in a sorted fashion. So if we look at the example that we have in front of us, we're going to want to start with the leftmost subtree and process all of the nodes in order, proceeding all the way over to the rightmost subtree. So we're going to go from A to P in processing. So we begin by starting from the root and then processing down the leftmost subtree until we get to the lowest value within the tree, and then working our way backwards. So traversing this tree, whether iteratively or recursively, is going to go in this fashion. A will be processed first, then D, and then it's going to go and visit its right node. And so it visits F. Now, the F is a subtree on its own, and it's going to examine its left pointer, find out that it's null, and then it's going to come back and examine its right pointer. H is a leaf, and so it's going to work its way back up the tree until it hits the root node, because all of the left-hand subtrees have been processed. And now it's going to follow the same process. It's going to drop down to to K, because that's the next value in line. It's going to process the root or the base node of that subtree, then examine its right-hand node, and then again, because the M node does not have a left pointer, it's going to go and process the P. And so that's in-order traversal. If you traverse your tree in that fashion, you're going to get your data output in sorted order. Pre-order traversal works a little bit different. It visits the root node first, and then each of the subtrees within the binary tree. The process for a pre-order traversal, again, can be done recursively or iteratively. It visits the node, traverses the left, and then traverses the right. So in this case, we begin with I, because that is the root node. So it's going to process the left tree. It's going to go and process D. And then the next element that gets processed is the A. and then the right-hand side of the tree is F. And then it's going to process the left, which is null, and then the right, which is H, of the F subtree. The root node's already been processed, and so it's going to come up and examine the next subtree down from there. It's going to visit the left side, then it's going to visit the right side, and then it's going to visit the left side of the M subtree, which is null, and then it's going to visit the right side of the M subtree. So pre-order traversal gives you a view of what the trees look like. If you look at IDAF, you see that I is your root node, and then the first subtree that it encounters below that is the D subtree, the A on the left, the F on the right. Likewise, when it processes the F subtree, it shows that there are no nodes on the left and H on the right. So that's pre-order traversal. Then we have post-order traversal. Post-order traversal visits the root node after all of the subtrees have been processed. And so what we will find is that the root node is going to be the very last data element that comes out of this list. Again, recursively or iteratively, we're going to traverse the entire left subtree, then we're going to traverse the right subtree, and then visit the base node itself. So we start out here at A, and then we process the full right-hand subtree before working its way backwards to F and then to D. And now the root node's going to be the last node visited in a post-order traversal. And so we start over here on K, and then to P, the right-hand subtree all the way down, and then back to M, then back to L, and then I is the very last item visited. This is probably the most complex of the traversal methods, but depending on what problem you're trying to solve, this order has its application as well. As I've said in each of the examples, all of the traversal methods can be coded either iteratively or recursively. And in the case of traversing a binary tree, a recursion is the simpler of the two methods. And so we'll go look at a little code now. Traversal of the binary tree can seem to be intimidating at first until you actually write the code for the traversal process. It's there that you discover that traversing a tree, especially recursively, is really a very simple process as long as you have in your mind the algorithm for how you're going to approach the different subtrees. In this demo program, we do an in-order traversal of the tree, which is really very simple. That is, we go down and we process the left, we return back to the base node, and then we traverse the right of all of our subtrees. In doing so, we end up with all of the binary tree data displayed in sorted order. So it's a good way for taking your list that you have assembled and printing it out in a sorted fashion. So let's demo this real quick. I've got a breakpoint set already in the code, and you can see that the code recursively written is very simple. Go to the left, print it out, go to the right, recursively calling depending on which way you need to go. And so here we are. We're sitting on the root node. We have a left and a right pointer because this root has both left and right subtrees. And so our node is not equal to null. Our node value being the pointer to the root value. And so we step forward. We're going to check the left and recursively call, are you empty? No. Now it's null. So because the item is null, it returns back, prints the value out, and then reads the right subtree. So we can get a look. It hasn't printed yet. We can see that it's beginning to print out the list in alphabetical order. So it's basically just going to loop out until it reached a terminal point in the list, and then it's going to process the subnodes within the list. And in doing so, it's walking up and down the tree, processing complete subtrees. So Arizona, then California to the right of that, then back to Idaho, and now it's working its way down the right-hand side of the list. So the in order, again, recursively presented, looks like this. It's really very simple. Pre and post order are, again, relatively simple so long as you understand what it is you're trying to accomplish. So don't be scared of writing your traversal code.